Like binomial and Bernoulli random variables, a Poisson random variable is another type of discrete random variable because, again, with Poisson, we're focusing on a countable number of outcomes. So we'll always treat Poisson variables as discrete, not continuous. Now, the difference between a Poisson random variable and a binomial random variable, if we remember about the binomial random variable, we indicate a probability of success, and then we're looking for the probability of k successes in n trials. So a binomial random variable is always indicated this way, b of np, or sometimes capital X of np, where n is the number of trials we're performing. That's always a fixed number of trials. And p is the probability of success on any particular trial. And when we calculate probability, we're looking at the probability of a certain number of successes in those n trials. So if we're running n equals 20 trials and our probability of success is 30% or 0.3, then we could go on to calculate probability around seeing any number of successes from k equals 0 successes all the way up to k equals 20 successes since we're running n equals 20 trials. But with the Poisson variable, we have this idea that the rate of occurrence of some event or object or something that's going on per unit of something else we call lambda, this Greek letter lambda, and then we're looking for or we're investigating probability of a certain number of occurrences or successes over one unit where these two units are referring to the same thing here. So an example could be the number of planes that fly over our house per hour of the day, where the occurrence there is a plane flying over the house and the unit is time, in particular hours. And so if we say that lambda is equal to 10 planes per hour, then we could investigate the probability of any number of planes flying over the house in 1 hour. But we can pick any kind of occurrence, and this unit doesn't have to be a unit of time. For instance, we could count the number of dogs that we pass per city block that we walk. And maybe on average, we pass 1.5 dogs for every block that we walk. And then we could investigate the probability of passing any number of dogs, 0 dogs, 3 dogs, 17 dogs in any one city block. So again, this occurrence can be really anything we can imagine. And these units here can be distance, they can be area, volume, time, any kind of occurrence per unit could, in theory, be modeled by a Poisson random variable as long as we meet a certain set of conditions. And those conditions are these 5. So again, we're looking for occurrences in an interval. We have to be counting a certain number of occurrences or events over some other interval unit measurement. That's what we described here. That's the first condition we have to meet. We have to be able to say that the mean is constant for each interval or each unit that we choose. So in our earlier example where we talked about planes passing over the house, this second condition might not hold because maybe planes only fly between certain hours of the day, maybe 6 a.m. and 10 p.m. And so if we're looking at a 24-hour period, this mean is not constant across each interval. We only want to define a Poisson random variable when all of the intervals we're investigating, as far as we know, at least theoretically, can have the same mean. We also need the count of occurrences or events in each interval to be independent. So we need to be able to say that the number of events that we count in one interval in one unit doesn't affect the count we get in the other intervals. Our counts need to be independent across intervals. And if the count we get in one interval means that we're going to get a smaller or larger count in the next interval, then we don't have independent counts. We wouldn't meet this third condition. We need to have non-overlapping intervals. So if we're counting planes passing over the house per hour, we can't overlap our hours. So if we count planes from 9 to 10 a.m., then the next interval would be 10 to 11 and then 11 to 12. We can't count planes from 9 to 10 and then treat 9:30 to 10:30 as another interval. Those intervals would overlap. And then finally, we have to be able to say that probability is proportional to interval size, which just means that if we determine that the rate at which planes pass over the house is, let's say, 10 planes per hour, then we need to be able to expect that in any 2-hour interval, we should see 20 planes pass over the house. In a 3-hour interval, we should see 30 planes pass over the house. So that probability, that mean or rate, lambda, should scale up or scale down as we scale up or scale down the interval size. If all of these things hold, then we can model the situation with a Poisson random variable and its associated Poisson distribution, and we can use those two things to calculate probability of a certain number of k successes per unit or per interval. Now, when it comes to calculating probability, here's what that looks like. Our probability formula for the probability of k successes in one unit or one interval is lambda to the power of k, where k is an exponent here, multiplied by e to the negative lambda. So negative lambda is the exponent. This value e here is Euler's number. Technically, it's a constant. It's equal to about 2.7 approximately, but it's an infinite decimal number. Any calculator you use will have a button for Euler's number. And then we're dividing by k factorial. So just to see what this looks like, let's say we're taking an example where we have a customer support team that receives a certain number of email support tickets per hour, and they're responsible for processing those support tickets. Maybe we'll say that they receive on average 4 support tickets per hour such that lambda is equal to 4, and we then want to investigate probability around the team receiving 0 support tickets in an hour, 1 support ticket in an hour, 2 support tickets, etc. Well, if we first check to see that this is a Poisson process, let's bring back our criteria here. We are in fact looking for occurrences in an interval. We're looking for a certain number of email support tickets per hour. So we have email support tickets in an interval of time. That's the kind of situation we're modeling, so that checks out. We're saying, based on data that we have, that the mean is constant in each interval. Maybe we have a global company, and on average, we do get about 4 support tickets per hour, and that doesn't fluctuate significantly from 1 hour to the next, so we meet that condition. We'll say that the count in each interval is independent because the support tickets we receive in 1 hour don't necessarily indicate that we'll receive more or less support tickets in the next hour, so the interval counts are independent. Our intervals are non-overlapping because we're going to look at each hour of the day without overlapping those hours. So we'll start maybe at the 8 o'clock hour in the morning, then we'll look at the 9 o'clock hour, the 10 o'clock hour, 11 o'clock hour. We're not going to overlap our intervals, so we'll hold to that. And we'll say that probability is proportional to interval size, because if we're getting about 4 support tickets per hour, we can expect 8 support tickets every 2 hours, 12 support tickets every 3 hours, roughly. So we'll say that we meet this condition as well. So that's kind of the idea there. If we say that this situation can be modeled by a Poisson random variable, then here's what probability looks like for this situation. So starting to calculate probability, what we want to look at is the probability that this customer support team gets 0 support emails in an hour. Well, in that case, k is equal to 0. We already said that on average, the support team receives lambda equals 4 support tickets per hour. So with lambda equal to 4 and k equal to 0, we make substitutions into our probability formula, and we say that we get 4 to the 0 multiplied by e to the negative 4 divided by 0 factorial. Remember that 0 factorial is equal to 1. We can use a calculator to find this value. If we round to 4 decimal places, it's approximately equal to 0.0183, or just under 2%. So there's a slightly less than 2% chance that the customer service team will receive exactly 0 support emails when on average they receive 4 in an hour. So slightly less than 2% chance that they'll receive 0 in any given hour. And then we keep everything else the same. We just change the value of k from 0 to 1, and then to 2, and then to 3. And these are the probabilities we get that are associated with the service team receiving exactly 1 customer support ticket in any given hour, exactly 2 tickets, exactly 3 tickets. And what you can see is that as we get closer to the lambda equals 4 mean value, the probability is rising. So since lambda was equal to 4, the further we get away from 4, the smaller probability we expect to see. So the probability that they get 0 tickets is just under 2%. The probability that they get 1 ticket is a little over 7%. The probability they get 2 tickets is about 14.5%. And the probability that they get 3 tickets is about 19.5%. And then if we calculate probability for exactly 4 customer service emails, and then 5, 6, 7, 8, we see that the probability that they get 4 emails is about 19.5%. And then, just like we saw on this side of lambda equals 4, on the other side of lambda equals 4, we see probabilities start to drop off as well. And if we plot these probabilities in a distribution, what we see is the Poisson distribution, or the probability mass function that's associated with this discrete random variable, this Poisson discrete random variable. And it makes sense that if lambda is equal to 4, we see these higher probability values clustered around that mean value of lambda equals 4. And then on both sides of lambda equals 4, the probability tapers off or decreases in both directions. Now, realize here that on the left-hand side of lambda equals 4, we stopped at 0 because, of course, it doesn't make sense to calculate the probability that the customer service team receives -1 emails in an hour. That's nonsensical. The fewest emails that they can receive is 0 emails. So that's sort of the left-hand bound of our probability distribution. But on the right-hand side, the distribution is unbounded. So we could have actually continued to calculate the probability that they get 9 emails, 10 emails, 11 emails, 12 emails, etc. on to infinity, and we could have found smaller and smaller and smaller probability values forever. But because those values get so insignificant, at a certain point, it makes sense just to cut it off. So this last value that we calculated here was the probability that k is greater than 8. We calculated the probability that they receive exactly 8 emails. And then instead of calculating the probability that they receive 9 emails, remember that because probability always sums to 1, we took 1 and then we subtracted all of these values that we calculated up through k equals 8. So we took 1 minus 0.0183, minus 0.0733, minus 0.1465, etc., continuing to subtract values all the way until we got to this last value and we subtracted 0.0298. And the result of subtracting all of these values from k equals 0 to k equals 8 from 1 was 0.0213. So the remaining probability, the probability that they receive 9 or more emails in any given hour, the probability that they receive 9 emails or 10 emails or 11 emails, all the way on to literally an infinitely large number of emails, all that probability summed up together is a little more than 0.02 or 2%. So there's just over a 2% chance that they receive 9 or more emails. And we've summarized that here with this last line, and we've also summarized it here in the distribution to show the probability that they receive 9 or more emails in any given hour. So those are the conditions under which we would use a Poisson random variable and how it differs from the binomial random variable we looked at earlier. And then this is the formula we use to calculate probability of k successes in any of the intervals that we defined, and then how to take all of those probability calculations and use them to create the Poisson distribution for the Poisson random variable.